Hi everyone, my name is Qianqian Wang. It's my great pleasure to introduce our paper, Tracking Everything Everywhere All at Once. Understanding motion in videos is fundamental for interpreting the world around us. However, existing motion estimation solutions are still limited. Feature tracking methods offer long-range correspondences, but only for a few sparse pixels, whereas optical flow methods provide dense correspondences, but only for adjacent frames. This raises the question, how can we completely capture the motion of all pixels throughout the entire video? Our work addresses this problem by introducing a new test time optimization framework for motion estimation. Given an input video and imperfect motion estimates from off-the-shelf methods, we optimize a global motion representation called OmniMotion that offers a complete description of the motion in the video, can track through occlusion, and maintains spatial temporal coherence. OmniMotion can produce full-length motion trajectory for all points in the video. Note that here we only show motion trails for some of the points, and the underlying representation captures the motion of all points. So, how might we represent OmniMotion? An ideal solution would be to recover a complete description of the underlying 3D scene and its motion. 2D motion could then be easily computed by lifting a point into 3D, applying camera and scene motion, and then projecting it back into 2D. However, solving this inverse problem is challenging and may not even be necessary for modeling 2D motion. Can we simplify the problem while preserving the benefits of an explicit 3D representation? Our first insight is that it's necessary to model motion in 3D to handle occlusion. In this example, the person's foot is occluded in the second frame, and both the foot and its occluder occupy the same 2D pixel. Having a z-dimension is necessary to tell apart surfaces at the same 2D location and naturally handles occlusion. Although this is a 3D representation, we actually don't need accurate 3D geometry as long as the depth ordering is correct. Second, since all we care about is 2D correspondence, it turns out that we don't need to disentangle camera and scene motion, and can model the two as a single transformation. Considering these two frames, the mapping function between their corresponding 3D spaces can be modeled as a bijection, or in other words, an invertible function. Given these insights, we propose to represent OmniMotion using a quasi-3D canonical volume and a set of local to canonical bijections. Each bijection is parameterized as an invertible network that can map 3D locations in the local coordinate frame to the canonical frame and vice versa, subsuming the effects of both camera and scene motion. The canonical 3D volume is a NeRF-like representation that stores the color and density of the scene. We call it quasi-3D since it's not an accurate reconstruction of the scene. As a whole, this representation ensures global cycle consistency and allows for tracking through occlusions. To compute correspondence, we use a rendering process similar to NeRF. Given a query pixel in frame I, we sample a set of 3D points along its ray. We map these points into the canonical frame and back to frame J to get their corresponding 3D location in frame J. We also get their density from the canonical volume, which can be used to alpha composite all of the mapped 3D location to a single location in frame J. Finally, we'll project it to 2D to get the corresponding 2D location. To optimize this representation, we primarily supervise the predicted correspondence to match their input motion data, for example, from an off-the-shelf optic flow method like Raft. Here, we show tracking results on the foreground moving person. Our method not only produces accurate long-range trajectories through occlusions, but also identifies occluded points, which are illustrated as crosses. The pseudo-depth visualization shows that our method learns a meaningful quasi-3D space with reasonable surface orderings without any explicit 3D supervision. Here we show some more results from our method. In the paper, we also include qualitative and quantitative comparisons showing that our method consistently outperforms existing baseline methods in tracking accuracy, occlusion accuracy, and temporal coherence. Thank you all for listening. Please stop by our poster or check our webpage for more details.